In this video, you'll learn about generalized linear models. This is the most popular type of model that's on exam PA. We're going to have some fun in this video. Get out your RStudio notebooks and get ready to follow along with the accompanying exercises. The learning objectives for GLMs are quite broad. This video will cover all of the topics. You'll learn to implement ordinary least squares regression in R, understand the specifications of the GLM and the model assumptions, create new features appropriate for GLMs, interpret model coefficients, interaction terms, offsets, and weights, select and validate a GLM appropriately, explain the concepts of bias-variance, model complexity and the bias-variance tradeoff, and select appropriate hyperparameters for regularized regression. So to begin, what are the assumptions of ordinary least squares? You might remember these already, but just as a review, the two assumptions are, number one, you say that there's a random component called y given x, and this is normally distributed, which has a mean that's equal to the expected value of the response variable given x. So this means that you assume that if you look at a histogram of your target y, that this is centered around 0. Well, it doesn't have to be centered around 0. It's centered around some mean mu, and it's approximately normal distribution. So it's symmetric, and it contains values from negative infinity up to positive infinity. Number two, you assume that there's a link between the linear predictor and the target. So you say that the mean of your data, which is actually a function of your data, is equal to x times beta, where x is a matrix. So this is beta 0 plus beta 1, x1 plus beta 2, x2 plus however many predictors you have. So this is also called the systemic component, because it is determined by your data. And this is known as the random component. Because you're dealing with a random variable y. Another way to say this is that the response y conditioned on x, it's normally distributed. That's a multinormal distribution with mean x beta and variance covariance matrix sigma squared times the identity. If you're not familiar with this matrix notation, that's totally fine. So you've already been familiar with these types of models before. Now, what you've seen is that if you have data that's like this, where the response is right skewed, you would then apply a log transform, and so it's more symmetric. Or sometimes you would take like an inverse, like 1 over y. That is only the case for ordinary least squares. For GLMs, we don't need to ever apply a log transform, and you'll see why. So that's a very common mistake that everyone makes when they're first learning about GLMs. So what are the assumptions of GLMs? So these are, number one, that you say that y given the data x is some exponential which can be binomial or Gaussian or gamma, etc., and that there's some link that you call G, where G is a function of the linear predictor. So you say mu of x is equal to x beta. So this is the mean of the response y. So if this is gamma, you know, with let's say y follows gamma of two parameters alpha and beta, then that means that the mean of y is just alpha times beta. So you'd say that mu is equal to alpha times beta. So what does that mean practically? Well, let's say that you had two people. You had me and you had someone else named Bob, and you're modeling costs here, right? You say that cost overall follows a gamma distribution. So if you look at like the histogram of all of the costs, it would look like this. Right, where you could fit like some gamma distribution to that. So my costs, you know, might be, let's say it's like healthcare costs. It might be 5,000 per year, or in Bob's costs might be only, I don't know, it might be 30,000 per year, right? So what this doesn't say is that these have to be numbers from the same distribution, but what it does say is that Sam and Bob both have costs that follow a gamma distribution, and mean, you know, might be something like 4,500, and Bob's average or Bob's mean cost might be something like 25,000, right? And so what the model allows you to do is to fit different means for each observation in the data set. So you'll see notation like mu I equals equal to you know, AI or BI, because I is the indicator for each observation. So that's what you mean when you say you conditionally adjust Y for the data. So what are the types of link functions G that are possible? So we talked about this mysterious function G. Well, the most common one that you haven't even been aware of is called the identity link function. And this is just where you say that the linear predictor, x beta, which we're going to just call z, is just equal to the mean. And so this includes all negative numbers and all positive numbers, right? So that means that you allow for your linear predictor to be any negative or positive number. The log link function has an inverse that's the exponent. And so, you know, an exponential function only allows for positive numbers. There's also the inverse link, which allows for negative and positive numbers. The inverse square, which allows only positive numbers as well. So the other key decision that you need to make when you fit your GLM is the response family. So these are the exponential family of distributions. And you know that each of these has a different shape and they have a different range, right? So your assumption is that G of mu is equal to x times beta. So you're saying that G inverse of x beta is equal to your mean, right? And so what you need is that this range of mean function, the range or the output needs to correspond with the range here, right? So a Gaussian random variable can have a mean that's positive or negative. And so the identity link function makes sense because this allows for negative or positive values. You could also use a log link function because that would just force the mean to be positive. But what you can't do is you can't take like an inverse Gaussian response family, which has only has positive values, and then use like an inverse link, which allows for negative numbers, because you'll be trying to define an inverse Gaussian random variable which has a negative mean, which is just nonsense. You should never take the log of y with a GLM. As you learned from ordinary least squares, you often take the log transform of y when the data is right skewed. But don't do this when you're using a GLM. The reason is that we have a better alternative, and that's to use a log link function. So you should be aware that these two models on the left and right are very different. On the left, the target is y, and the response family is Gaussian. So this is saying that the response y has a Gaussian distribution, and the mean is equal to the log of x. On the right, it's saying that the log of y has a Gaussian distribution, and the mean is an identity. If you look at the output from these models, you'll see that they're different. The AIC here is positive. The AIC here on the right is negative. Another way to think about this is the mean of the log is not the log of the mean. So consider this scenario, okay? You're collecting samples from men and women to find out if there's a difference between their blood pressure, right? You want to be able to say, do men have higher blood pressure than women? You have two sampling methods. The first is that you collect blood pressure from 10 women and then take the average, and then collect blood pressure from 10 men and take the average. Then you compare the log of the first average to the log of the second average. And the second scenario is that you collect the log of blood pressure from 10 women and then the log of blood pressure from 10 men, and then compare the averages. Now ask yourself this question, okay? What happens if there's one man in the first scenario that has very, very high blood pressure? Then when you collect the blood pressure from these 10 men and take the average would be skewed, right? It would be skewed by that one outlier. So then if you compared the log of the first to the log of the second, there would likely be a difference. On the other hand, in scenario B, if you collected the log of blood pressure from this one man who had very high blood pressure, that log would be would make that number smaller, and so when you add it together with all of the other logs, it would not have nearly as much impact, and the difference between the blood pressure for men and women would be much smaller. So you can create your own GLMs. Often you are fitting a model to data, but you don't know where the data came from, right? It comes from real life. It was collected in a scientific study. You don't know what the equation of the data is. It could be a person's healthcare costs, or the likelihood that they're in a car crash. So there's a lot of information that you don't have about the person, and you're just trying to fit a model to get a best estimate. But in this case, you can perfectly understand the data using simulation. So if you understand the assumptions of a GLM, you can recreate those on your own. Then you can try fitting different models and see how your assumptions change the model's performance. So to start, you'll say that g of mu is equal to x beta. Then you apply the inverse link function to both sides of the equation. So this is the mean of the response is equal to g inverse x beta. In the case of the log, this just is the exponential equation. In R, you can use this function to generate a random normal variable, and the mean is equal to 10 plus x. So I'm just adding 10 to the value of x because x is uniform on -1 and 1, and I want this exponential term to always be positive. The reason why is because I want all of my y values to be positive numbers so that I can apply the log link function. So this is using a Gaussian random variable, and the Gaussian could be either positive or negative, right? The support is negative infinity or positive infinity. But if you have a very high number, like e to the 10, then it's very, 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 very unlikely that you will ever generate a negative value, which is why this is just adding the value of 10. So if you fit this model, you'll see that it's perfect. You'll see that the predicted values against the residuals show no pattern, which is what you expect. They're scattered about 0. You'll see that the theoretical quantiles perfectly match the observed quantiles in the QQ plot. This means that all of the points lie along a 45-degree line, which is perfect. You'll see that the predicted values against the square root of the studentized Pearson residuals also show no pattern, and that there are no points which have too much leverage in the residuals versus leverage plot. So for here, you want to see that the residuals are all centered around 0, and that there aren't any points that are significantly above or below this line. On your own, try out other link functions. In the notebook provided, make changes to this function g. You'll want these to be other functions of the mean, such as well, you already looked at the exponential case. You can also look at the inverse square, or the square root. So compare how these models look, and you can also change the response family. Change the name of family here to either Gaussian, binomial, gamma, inverse Gaussian, or Poisson. You can compare the different combinations of response family and link function. What happens if you fit a model that's incorrect? What if you fit a log link function with a gamma response to data that was generated with an inverse link and an inverse Gaussian distribution? Or what happens if you fit a Gaussian response family with a inverse square link to data that was generated from a Poisson distribution using a inverse square link? Try out other combinations and figure out when R lets you fit the model. Sometimes it will say algorithm did not converge, or please supply coefficient starting values. Sometimes it will not even work because the range of the mean does not match the data. In other words, you might try to take the log of a negative value, which isn't possible. You can also change the values of the coefficients. So here's an example of how you would simulate data with multiple predictor variables. You'd say that the mean is equal to x1 plus x2. and then you fit a GLM. And if you change the values of these coefficients, let's say it's 5 times x1 plus 20 times x2, and then you fit GLM, you'll see that the coefficient estimates match what you supplied. As in this case, you can see the estimate of the first is 5, the estimate of the second is 20. So as a challenge, I want you to create a GLM that has an interaction term between x1 and x2, and then compare what happens if you fit the model that contains the interaction or which doesn't contain the interaction. Second, I want you to fit a GLM that has two new predictors that are the squares of x1 and x2. And what happens if you omit these from your model? Or conversely, what happens if you try to include square covariates that don't really exist in the data? Then multiply by 0.91 and so forth. So the model for this is that you have the log of mu is equal to beta 0 plus beta 1 times gender male plus beta 2 times age 10 to 20 and so forth. And you just call these like x1, x2, x3, x4. So these are binary, either 0 or 1. And then these down here are just continuous numbers. So when you apply the exponent to both sides, you get your mean is equal to e to the beta 0, which is 0.8, times e to the minus 0.03 times x1 times e to the minus 0.1 times x2 times up to, this is x1, x5, 6, 7, 8, 9, and this is 0.04. However, this is the number of diags, and so you actually multiply by the number of diagnoses. So let's call this num diags. And so take the product of all of these things, and you can interpret this as a set of rules. You start with a mean prediction of 2.2 days. If the patient is male, then this is 1. And so you multiply by e to the negative 0.03, which is 0.97, etc., etc. When you get to num diags, you just multiply by 1.04 to the n. So the final method of interpretation is the probability modeling method, or the example cases method. The easiest way to, so this is basically where you run a bunch of examples through your model, you change one input at a time, and you see how that changes the output. So here's an example. You are using predictors age, years of education, internet network, hours worked per week to predict if the person's high profit or low profit. So let's look at the first person. They're 39 years old, 12 years of education, and let's say that they're connecting on a mobile network that's 4G LTE, and they work 35 hours per week, and their probability of profit is 60%. The next person's 53, 18 years of education, also on 4G. They work 40 hours per week, and their probability of high profit is 45%, and so forth. So you could compare like different cases. Like you can compare this person to this person. So you could create new examples and run them through. So this person has 16 years of education as well. They're also on the 5G network. They're also working 50 hours per week. However, they're older. They're 40 as opposed to 25. So you could make a rough estimate and say that the profit is higher for older people than for younger people. Ideally, you do this over more cases. You do like another 20 or 10 cases. You'd look at someone who's aged 25 and 35 and 40 and 50 to see if there's a consistent pattern. A small topic on this exam is, it's a small topic, but it's really three topics together, are interactions, offsets, and weights. So offsets have never appeared officially on an exam, although they are on the syllabus. Weights have never appeared on PA, but they're also on the syllabus. Interactions, though, have appeared, and they will continue to on June 2019, December 2019, and in June 2020. So it's most likely that these will be on every exam PA in some way or another. So what is an interaction? It's when the impact that a predictor has on the response is different depending on another predictor in the model. So you just basically have to remember this definition, and it's easy to do so by thinking of this picture. So let's say that you're modeling a variable y, and you have one predictor variable, which is equal to color, and you have one continuous variable. So the way to interpret interactions is just that it's a way of changing the effect that a variable has depending on another variable in the model. So in this case, you say that the impact that x has on y is the same for blues as it is for reds. On this case, because there's an interaction here, this is the interaction term right here. Because of this interaction term, there's a different impact for red values as opposed to blue values. So here you can see that there are separate lines for each of the car types, which means that there's an interaction between the claim amount and the car type. If there was no interaction, then what you would have is one line for all of the car types. So that would just look like this. So this would be your regression line, and your regression line wouldn't change for pickup trucks or sedans or sports cars and so forth. An offset is convenient in certain situations. It's a way of applying a constant term to the linear predictor. So in your linear model, you have your intercept term, and then you have beta 1 times your first variable, and a bunch of other coefficients times your other variables. Well, sometimes you just want to increase this by a certain amount. And the way to do that is with what's called an offset term. You can also think of this as being a predictor variable which always has a coefficient of 1. If you multiply anything times 1, you'll just get back the number itself. So on this exam, though, you only need to know like a very specific case of offsets. And that's because actuaries only use offsets in very special ways. The three assumptions that you need to know are that the family is going to be Poisson, the link is equal to the log link, which is something called the canonical link function, which basically means that it's more likely to converge, and it's statistically convenient to use that link. And finally, you need to know the offset. So the offset is usually going to be the exposure unit, which in insurance cases will be like the length of the policy period, or the number of the number of cars that you're insuring. So the key differences are that both account for exposure, such as the length of the policy period, the number of miles driven, and so forth. But they're used in different ways. So like, let's say our example, you're fitting a model to predict the total claims, the severity. So your target is average claims. So this would be like average claims per member per month. The weights could be member months. And so that member months is equal to number of members, number of people, times like total policy months. And when you multiply the target variable times the weights, you get total claims, because you multiply average claims times member months, right? The second example is that you predict the number of claims, which is the frequency. So in this case, your target would be the number of claims, or claims per member per month, and then your offset would be member months, would be the log of member months. Now this is because you're modeling a frequency, which is a count of claims. And so this implies that y is Poisson. And so that's one of the examples of where you'd use the Poisson. So this is one of the big topics of the exam. And you tried out answering questions in different ways to see what would increase and decrease your score. Have you ever wondered how they calculate that probability? You get a score that's like 850. But how do you convert that to a probability of defaulting on a loan? One really naive thing to do would be to just take 1 minus 850 over 1,000 and then say, okay, if you have a credit score of 850, it means that you have a 15% probability of default. Is there a more mathematical way that this can be done? Well, let's look again at what happened here. So you had all of these questions, and you had these variables. So these coefficients here are the beta values, and Sam's values here are the x's. And then when you take the product of these two, this is your linear predictor, beta x beta. And so what you have here, the value of this linear predictor, this is just 5 times 4 plus 5 times 4 again, plus you just take the product of all these numbers and you get 16.37. And then I applied this weird transformation where I said p is equal to the exponent of z divided by 1 plus the exponent of z. And then that gets a probability that's 2.6%. And I said, okay, I took 1 minus that number times 1,000, and I got some credit score. So what actually is going on is that it's translating a number to a probability. So this, on the x-axis here, you see the linear predictor. This can be any real number. On the y-axis, you see a probability. It's between 0 and 1. And there are different functions that can do this. The most common is called the logit. And the logit transformation, which you also hear about with logistic regression, says that z is equal to the log of p divided is equal to the log of p divided by 1 minus p. This is also called the log of the odds. So the odds of something happening are the probability that it happens divided by 1 minus that probability. So on a piece of paper, you can try this. Try to find the inverse of this function. Remember, to solve for an inverse, we just try to move all of the p's to the opposite side of this equation. So you'd take the exponent of both sides. You'd say exponent of z is equal to p over 1 minus p, and then you multiply both sides. 1 minus p, and these cancel out, and then you get e to the z minus p e to the z is equal to p, and then add p e to the z to both sides, and this gets e to the z is equal to p plus p e to the z. It's equal to p times 1 plus e to the z, and this is e to the z, and so this gets p is equal to e to the z divided by 1 plus e to the z. So this is the way to translate between a probability and a linear predictor. There are other link functions. So you just saw the logit here, but the probit actually takes z and applies an inverse Gaussian CDF. And so you basically use a Gaussian CDF, apply that to your linear predictor, and then you get the probability. The Cauchet distribution uses this fancy trigonometric function. And this function doesn't have an easy inverse. Another is the complementary log-log, which also does not have an inverse. So there are some different properties of each of these. You can read over them on the cheat sheets. Mostly, though, the probit and the logit link functions are used on this exam. So how can you interpret the probabilities? So if you have any of these link functions other than the logit, there's not an easy way to take the inverse. And so even with the logit, there's not an easy way to take the inverse. But one easier method that works for any link function is called the probability modeling or example cases method. So here's an example. You have data on a person's age, their years of education, whether or not they're connected with their smartphone on 4G or 5G network, and their hours worked per week. And then you're predicting the probability that they're high profit. So if you wanted to measure the impact that age has on the profit, you could just add in example cases where you change the age variable. So this person here on the bottom is the same as this person, except for their age, right? They're both, they have 16 years of education. They were both using a 5G network. They've both worked 50 hours per week, but this person is 40 instead of 25, and they have a higher probability of profit. So this so far has appeared on 2 exams, and the SOA will give you template code to do the coding. But what you need to do is interpret the result. So you will get a table like this, and you'll be able to tweak different values, and you need to change the values and then see how the outcome changes. Interactions, offsets, and weights. These are three very, very different things that often get mixed together. Offsets have never appeared on exam PA, but they are on the syllabus. Weights have also not appeared on the exam. Interactions, however, have appeared on every exam, and they will continue to show up. They're not limited to linear models. They're also in decision trees, random forests, gradient boosted machines, and so forth. So what is an interaction term? An interaction is when if the impact that a variable has on the target changes depending on another variable that's in the model. So let's take this example where you're predicting y and you're using an input variable. So this is x2, and then x1 is the color. And so your equation is y is equal to beta 0 plus x1, which is a number, which is the color, plus x2, which is some number, plus the interaction term, which is x1 times x2. And what happens is that when the color is equal to blue, then x1 is equal to 1. When the color is equal to red, x1 is equal to 0. And so what happens is that when x1 is 1, this is your equation, and you can rewrite this as beta 0 plus beta 1 plus, and then factor out the beta 2 and the beta 3. 2 plus beta 3 times x2. And you can actually think about this as being some beta 0 star plus beta 1 star times x2. So this is a new intercept term, and this is a new slope, right? So what this says is that the slope for blues is different than the slope for reds when there's an interaction present. If there's no interaction, then the model does not make a distinction. So your regression line would just look like that. Another instance, so let's say that you are predicting the log of the Blue Book value, which is the Kelly Blue Book value, which is a measure of the car price, and you're using the log of the claim amount as the predictor, and you interact that with car type. So car type could be a truck, a pickup, a sedan, a sports car, and so forth. If you say that there's an interaction in the data, it means that if you fit a separate line for each car type, that the slopes of those lines would be different. And in this case, you can see the green line here is steeper and it's positive, whereas the slope of panel trucks is basically flat, and so forth. So if you had no interaction, you just have one big regression line like that. In certain situations, it's convenient to include a constant term in the linear predictor. This is the same as including a variable that has a coefficient that's equal to 1. Right? Because if I just multiply this offset term times 1, I don't change it. So you could think of this as another beta. Well, it's technically possible to use offsets in a variety of ways. On exam PA, you only need to remember this one example, and that's when the family is Poisson, the link is log, and the offset is going to be the exposure. This will just be the number of policy periods. So as an example, let's say y is equal to the number of COVID cases, and your exposure, call it W, is equal to the number of people exposed to the virus. Then if you use a Poisson model, because you're modeling a count, the number of people who have COVID, then you have the following. You say you're modeling the expected value of number of COVID cases divided by number of people. Number of people exposed, right? So this is modeling a rate. It's the infection rate. So it's the expected value of y over w. And when you use the log link function, you say that the log of the expected value of y divided by the expected value of w is equal to your linear predictor, x times beta. And property of the logs is that you could rewrite this as the log of the numerator minus the log of the denominator. So it's log of expected value of y minus log of expected value w equals x times beta. And then you move this to the right hand side and you have log expected value of y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus up to log expected value of w. And this term right here is the offset. It's known in advance, and so it's a constant value because you already know how many people are exposed. So you don't actually need the expected value. It's just the log of w. So what are some of the ways that offsets are used versus weights? Both use exposure. That will be the length of the policy period or the number of miles driven and so forth. However, with Poisson, you're going to use, so when you, remember, when you use an offset plus log link, then you're going to take the log of the exposure as the offset term. When you use weights, you don't need to use a log. An example is if your goal is to predict the total claims, the severity, then your target can be the average claims or claims per member per month, and your weights are just the member months. Then you take the target times the weights and you get average claims times member months and you get total claims. If you do this in R, if you have like target as average claims and then you specify weights, when you use the predict function, it will automatically multiply these two together. So you don't have to do that. An example of Poisson regression with an offset is if your goal is to predict the number of claims, the frequency, your target is the average number of claims per member per month, then your offset is going to be the log of the member months. It's not written here, but your link function would also have to be the log. Let's say that you asked an actuary and a mathematician to draw points between these lines. The bias-variance trade-off is an important topic in machine learning, and it does come up on this exam. So consider the following example. You ask an actuary and a mathematician to draw a line connecting these points. So a mathematician might look at this and say, well, this curve looks to be quadratic. So I'll fit a polynomial. And my polynomial will look like this. And if I look at the r squared term, this might be very high. It might be 0.9. So you could look at this and say, wow, this is a great fit. But if you asked an actuary, they might suggest that you just use a straight line. And your r squared might be a little bit lower because the distance between the line and these points is greater, right? The blue line might be a closer fit, but what it doesn't account for is new data points. Like, what if there's a data point that's out here? Then the straight line will do a much better job of making a prediction. What if you have an x value of 50, right? Your blue line prediction will be like negative, but your red line will be up here, which is going to be most of the time a better estimate. So this is an example of why the bias, variance, and trade-off is important. So what you just saw was an example of what's called overfitting. So what you were measuring when you looked at r squared was something called the training error. So the training error represents the model's performance based on your observed data. The testing error is your model's performance based on new data that you haven't yet seen. If you choose your model just to minimize the training error, often you will have very poor test error. So this graph shows you the mean squared error on the y-axis, and on the x-axis it shows the model flexibility. So you could think of this as the degrees of freedom. So in this case, you can actually think of the blue line as being a 2-degree polynomial, and the red line being a 1-degree polynomial. So the blue line is more flexible than the red line. So on the x-axis, you can think of this flexibility as being the amount by which the line adapts to fit the data. And basically, as you increase your model's flexibility, you decrease both the training and the testing error. But if you make your model too flexible, then your training error will continue to decrease, but your testing error will start to increase. This is also called the number of predictors in your model, or the variance of your model. Bias is not being complex enough to capture signal in the data. So to understand the bias-variance trade-off, you need to know about bias and variance. Bias is not being complex enough to capture signal in the data. So if your target variable is y, and your model's prediction is f of x, which is some function of the data, then the bias is equal to the expected value of y minus the expected value of f of x. The variance is the expected loss from the model being too complex in overfitting to the training data. So this is an example of overfitting, where you might come through and draw a line that perfectly connects the dots together, but then maybe makes like a absolute nonsense prediction for values that are outside of the range of the data, whereas underfitting would be making a line that's too simple, like just using a straight line when you know that there's perhaps some so there's some upward curve here. So this means that so overfitting is when variance is too high, and underfitting is when variance is too low. This is the same as saying bias is too high. So you can remember it like this. So the bias-variance trade-off relates bias to variance. It says that the mean squared error is equal to the variance of the model plus the bias squared plus the irreducible error. So we just talked about the variance and the bias. The irreducible error is the noise in the data. You might hear this referred to as white noise, or just random signal. So there are 4 different combinations. Imagine that you have a target and you're shooting arrows at this bullseye. You want to get as many arrows at the center as you possibly can. You have 4 possibilities. When you have high variance, it means that your shots are very spread out. When you have high bias, it means that your models are far away from the center. So let's say that this instance is high variance. So your shots are all over the target. And it's high bias, which means that you're not even aiming towards the center. So your shots might be down here. If you have low variance, then it means that your shots are all close together. And if you have low bias, it means that they're near the center. So this is the best case. It means that your shots are close together and near the center of the target. If you have low bias and high variance, your shots will be spread out, but they'll at least be centered. If you have low variance and high bias, it means that your shots could be like this. So the bias-variance trade-off says that when you tend to increase bias, you tend to decrease the variance. And when you decrease the variance, you tend to increase the bias. So this example of having low bias and low variance is the ideal state. And you can think of this irreducible error here as being this group right here. It's the amount by which you cannot improve any further. So consider these 3 examples. These are from ISLR Chapter 2, which you can read on your own. Chapter 2. So this is the mean squared error. And this is the variance of the model plus the bias squared plus the irreducible error. So the red line here is the mean squared error, and this is the sum of this bias plus the variance. So this model starts out with low flexibility, and then as you increase the flexibility, your MSE goes down, right? So your bias starts out high, but your variance starts out low. And then it reaches a minimum point, and then the variance starts to take over, and the bias just keeps going down. So in this case, the optimal model is right here. But depending on the data set, there could be other things that happen. Like you could fit a model that starts out at the optimal point, and as you increase the flexibility, you just keep increasing the variance, whereas the bias stays constant. Or you could have the reverse, where your model starts out with very high bias. So think of this as being a model that is just making, so this has low variance and high bias, and as you increase the flexibility, as you add more predictors, as you tune the hyperparameters, you decrease the mean squared error. So different models have different levels of flexibility, and that relates to how easily you can interpret the result. So as a rule of thumb, when you have high flexibility, it's lower interpretability. And when you have lower flexibility, you tend to have higher interpretability. So your decision tree, for instance, is the easiest to interpret, but if it's a simple tree, then it's also going to be inflexible. If you have a GLM with subset selection, you can at least remove variables, just like with the lasso. And so you have a simpler GLM, which is easier to interpret, but you lose some flexibility. If you just run an ordinary GLM by itself, you might get a lot of variables that are still difficult to interpret, but that gives you a pretty good starting point, which is why it's a good idea to always start with a GLM. And then you can either reduce the model complexity using like subset selection, or you can make it more flexible by using an elastic net. And then the most flexible models that this exam uses are tree-based models, bagging, which are GBMs, and bagging, which we'll talk about later, are random forest models. Boosting are gradient boosted models. And these tend to be the more powerful machine learning algorithms. They come at a cost. They're more difficult to interpret, but they have the best performance, and they work in the most diverse set of applications. So here's an example from June 16. Discuss the bias-variance trade-off. Define bias and variance and describe the bias-variance trade-off. Explain how lasso regression seeks to address the trade-off. Explain how splitting the data into training and test sets and calculating a metric such as the Pearson goodness of fit statistic on the test set seeks to address the trade-off. So this question was worth 7 points out of 100, and it doesn't ask you to do anything technical. You just need to explain the statistical properties using your own language. So this was the model solution from the SOA. And there's often not a single solution to these questions. You can still get full credit by providing your own explanation. So the way to be successful on this question is just to do exactly what they say. So you basically need to memorize the different definitions. So this first paragraph, bias is the expected loss caused by the model not being complex enough to capture the signal in the data. Variance is the expected loss from the model being too complex and overfitting to the training data. And so you can read through this entire answer on your own. So you just don't get too caught up in the technical aspects without practicing the explanation. So if you use flashcards, if you look at our exam cheat sheets, we have definitions for all of these statistical properties. Really practice writing them out, and so that when the time comes, when you see these questions, you'll be able to quickly type out your response without having to spend a lot of time thinking. The next topic is selecting hyperparameters for regularization. So this will talk about a few different models. These are all variations of the GLM. So the theory that we just outlined doesn't change. These are add-ons, ways of modifying the GLM. These are lasso, ridge, or elastic net, and step AIC. There's really no memorization needed for these. Fortunately, within R, you can always type in question mark function name in order to bring up the documentation. Like if you need to know about an elastic net, you can just load the library GLMnet and then type in question mark GLMnet. If you need info on step AIC, that's in the mass library. You just use question mark AIC or question mark step AIC. And I don't need to talk about them here in this video because the documentation is basically a Wikipedia page that has all of the info that you need. So quickly, let's go over the three shrinkage methods. So really the first method is just the ordinary GLM. So this is optimizing for the residual sum of squares. And so this is the sum of y minus your predicted y squared. So this is the same as minimizing the mean squared error, which is, in the case of ordinary least squares, it's also the maximum likelihood estimate. Then you have ridge regression. So what this does is it takes the RSS here plus the sum of the squared coefficients times a parameter lambda. That you also hear this referred to as the L2 norm. So this part here, this sum of the squared terms, is called the L2 norm. And the final version is called the lasso regression. And so this is the residual sum of squares plus a parameter lambda times the sum of the absolute values of the coefficients. And this is also called the L1 norm. So the important point is that for ridge regression, it shrinks the coefficients so they get smaller, but it never makes them exactly zero. And why does it do that, right? Why does it make the coefficients smaller? So typically what you'll do is you'll look at a graph of the residual sum of squares against the value of lambda. When lambda is really big, then this this term gets really big, right? And you want, let me rephrase that. On the y-axis, this is RSS plus lambda times the L2 norm on the y-axis. And so when lambda is really small, then there's less weight given to the squared coefficients. When lambda is really large, there's more weight given. And so if you look at a graph, you might see that as you fit models with different values of lambda, you get, you can find the point where the model's error is lowest. So how do you find the best value of lambda? This is called parameter tuning. The parameter is lambda, so you would be tuning the shrinkage parameter. The way to do that is to look at the test error across different values of lambda. So this would be test mean squared error on the y-axis. On the x-axis, you might fit models with different values of lambda. And you might find that there's a minimum point here when lambda is equal to a certain value of lambda. And so this would be your optimal model. And the same is true for finding the best value of lambda for the lasso regression. So when lambda is really large, the model has smaller coefficients. So that means that the flexibility is lower. Conversely, when lambda is really large, really small, the coefficients are larger, which means the flexibility is higher. So you can also think of like this graph as being the test MSE against flexibility. So it's actually like one of these graphs here. So this might be your value of lambda. The lasso regression is very similar, but in addition to just the graph of the test MSE against the parameter lambda, you can also look at a graph of the sizes of the betas on the y-axis against lambda on the x-axis. And what you actually will see is that if you had, and what you'll see is that when lambda is very low, the coefficients of the model are high. But then as lambda gets larger, the coefficients get smaller. And then eventually they equal 0. So you might have a model that has like 3 different coefficients. And they're each different colors. So this coefficient might start out negative and then become 0. This other coefficient might start out very positive and then eventually decrease to 0. And so if this model would have 1, 2, 3, 4 predictors. So it would look like y hat is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. So there's 1, 2, 3, 4 predictors. And as you increase your value of lambda, these beta values get smaller. And if lambda is large enough, then they become 0 for certain values. If I choose lambda right here, then all of the variables would actually be 0. All of the coefficients would be 0. And so your model would just be an intercept term. If you choose a lambda like back here, then this blue coefficient here would be 0. This yellow coefficient would also be 0. So you'd have two coefficients that were non-zero. So that's just another way that as you change the value of lambda, you make the model more or less flexible. There's something called the elastic net, which is actually the best of both worlds. So it takes so it uses a special error term. So it uses the residual sum of squares plus a weight of the L2 norm plus a weight times the L1 norm. So this will often result in the best performance of either the lasso or the ridge regression. You could tune this using a two-dimensional plot. So you tune this elastic net actually using two parameters. You have an alpha parameter and you have the lambda parameter. And so for each value here, you'd have a value of the mean squared error. You could find this best combination of alpha and lambda, which has the lowest model error. In the study guide, there is a quiz. There are two sections, one for ridge regression and another for the lasso. The two questions are, once you run the examples on your own, and you'll create all of the graphs that I just talked about, answer the questions. Number 1, how do ridge regression and the lasso improve on simple least squares? And 2, in what cases would you expect ridge regression to outperform the lasso and vice versa? So like, think about this. I'll give you two data sets. Data set 1 has n is equal to 10,000 records. Data set and p, the number of predictors, is equal to 500. It means there are 500 predictor variables. Data number 2 has n is equal to 5,000 records and p is equal to 5. Would you expect that the lasso or the ridge would be better on one of these data sets? Or what about this case? What about data set 3, which is which has 100 continuous variables and 2 factor variables, and data set number 4 that has two continuous variables and 100 factor variables. Answer these questions on your own.